spheres. Seriously, you see them everywhere. Huge stars, planets.
Right.
But then also tiny little dewdrops, bubbles floating past. It's just, this shape keeps showing up.
It really does.
And it makes you wonder, doesn't it, why? Why does nature, from the absolutely enormous down to the incredibly small, seem to just prefer the sphere?
That's a fantastic question. And you're right. The answer isn't just one simple thing, one law. It's more like a principle, really, operates on different levels, but it's deeply tied to these universal tendencies, you know, minimizing energy, finding symmetry.
Okay.
And what's really wild is how this connects the everyday physics we see, classical mechanics, with the really strange quantum world.
The probabilistic stuff.
Exactly, where matter isn't even solid stuff anymore. It's more like vibrations, wave patterns.
And that connection between the sphere shape and matter as vibration, that's what we're digging into today.
Precisely.
This is our deep dive, drawing from the spherical principle, from quantum vibrations to cosmic orbs. We're going on a journey, right? From the biggest things in the cosmos
All the way down
to the absolute bedrock of quantum reality.
Let's do it.
Okay, so let's start classical. Things we can sort of picture. You said the sphere is about minimizing energy. How does that work for, like, planets? Huge things.
Right. On that massive scale, gravity is king. It pulls everything inward towards the center of mass equally from all directions.
Okay, makes sense.
So if you have enough stuff, enough mass, the shape that lets everything get as close to the center as possible, the lowest energy state for gravity,
Is a sphere.
is a sphere. Every point on the surface is the same distance from the center. It's the most compact way gravity can arrange things.
And that's hydrostatic equilibrium.
That's it. It's this balance, gravity pulling in, and then some kind of outward pressure resisting it.
Like heat in a star?
Exactly, heat and radiation pressure in a star. Or just the structural strength of rock in a planet. Any other shape, anything deviating from that sphere would actually hold more gravitational energy. It'd be unstable in a way.
Oh, so, like, you couldn't have a planet-sized cube.
Well, not naturally. Imagine a ridiculously huge mountain range on a planet. The pressure at the bottom would be so immense.
It would flow.
Over millions of years, yeah. The rock itself would behave like an incredibly thick fluid slowly slumping down, trying to get back to that spherical, lowest energy state.
Okay, but what about asteroids then? They're all lumpy.
Good point. It comes down to mass. For smaller things, like most asteroids, their own gravity just isn't strong enough to overcome the basic electromagnetic forces holding the rock together rigidly.
Well, they just stay jagged.
They stay jagged, but there's a threshold. Get big enough, like the dwarf planet Ceres?
Ceres is round.
It is, because its gravity was strong enough to pull it into a spheroid shape.
But you said spheroid, not sphere. Why the difference?
right.
Rotation.
Exactly. Rotation throws a wrench in the works. As a planet spins, there's a centrifugal effect pushing matter outwards, strongest at the equator.
Like being on a merry-go-round.
Precisely. So you get this bulge around the middle. It's still trying to be a sphere because of gravity, but the spin flattens it slightly into an oblate spheroid.
Like Jupiter, doesn't it bulge quite a bit?
It does, almost 7% wider at the equator than pole to pole. And Saturn's even more extreme, over 10%, because they spin so fast.
Oh, wow. But slow spinners.
Like Venus, barely spins at all. And guess what? No discernible bulge. It's almost perfectly spherical.
Okay, that makes sense for the big stuff. Gravity and rotation. But now, zoom way down. Microscopic water droplets. Gravity is basically irrelevant there, right?
Totally negligible. Down there, the dominant force shaping things is surface tension.
Which is electromagnetism, basically.
Yeah.
Molecules pulling on each other.
Exactly. Think about a molecule deep inside the liquid. It's getting pulled equally in all directions by its neighbors.
Yeah.
But a molecule right at the surface, it only has neighbors below and beside it, nothing above. So there's a net inward pull.
Pulling the surface tight.
Yes. It creates this effect like a stretched elastic sheet over the surface, always trying to contract, to pull inward.
Like a balloon trying to shrink.
Kind of, yeah. And to minimize the energy stored in that stretched skin, the liquid needs to minimize its surface area for the amount of volume it has.
In the shape that does that best.
Is the sphere again.
No.
Minimum surface area for a given volume. That's why tiny water droplets, like in fog or if they're floating in space, just naturally pull themselves into near perfect spheres. It's their lowest energy configuration.
So the classic raindrop shape, the teardrop. That's wrong.
Pretty much, yeah. That's just how we draw them. A falling raindrop actually gets flattened on the bottom by air resistance.
Oh, right.
The pressure underneath is higher while the top stays curved. So they end up looking more like a hamburger bun.
A hamburger bun. Okay, I'll never see rain the same way.
And if they get too big, maybe over 4 millimeters or so, the air turbulence just rips them apart because the surface tension isn't strong enough to hold that bun shape together anymore. They break into smaller, more stable spheres.
Okay, let me get this straight. We've got giant stars shaped by gravity. We've got tiny water drops shaped by surface tension. Totally different forces, totally different scales.
Worlds apart, yeah.
But they both end up making spheres. What's the deep connection? What ties this together?
That is the crucial insight, isn't it? Despite the forces being different gravity on one hand, electromagnetism manifesting as surface tension on the other, and the scales being astronomically different.
The result is the same.
The result is the same.
Yeah.
A sphere. Because in both cases, you have forces that are essentially pulling inwards towards a center, acting isotropically, meaning the same in all directions, and the configuration that minimizes the potential energy under those conditions is the sphere.
So sphericity isn't just a shape. It's like a state of minimum energy.
Exactly. It's a physical state of equilibrium. And any deviation from that perfect sphere, like Jupiter's bulge or an asteroid's jaggedness,
It's telling you something.
it's information. It's a record of the other forces at play, rotation or the lack of sufficient gravity. The shape itself encodes the physics acting on the object.
Okay, mine's slightly blown by the classical world already. But now we need to go deeper.
Much deeper.
We've seen classical forces making spheres. But what happens when we zoom in so far that the idea of a solid particle just dissolves into that weird quantum realm?
Right. This is where things get really counterintuitive. We have to talk about wave-particle duality.
The idea that things can be both, a wave and a particle.
Yeah. Fundamental things like electrons, photons. They don't behave purely like tiny billiard balls, nor purely like waves in water. They show aspects of both, depending on how you measure them.
I remember hearing about the double slit experiment.
The classic. Young's experiment showed light-making interference patterns, undeniable wave behavior. But then Einstein comes along, explains the photoelectric effect.
Where light acts like little packets, photons.
Exactly. Discrete packets, particles of light. So, which is it? The debate raged for centuries.
Until de Broglie. He kind of unified it, didn't he? But in a really radical way.
He did. Louis de Broglie in 1924. He had this incredibly bold idea. Maybe it's not just light. Maybe all matter, electrons, protons, everything has a wave-like nature.
Everything. Like even us.
Technically, yes, though the wavelength for something as massive as us is so astronomically tiny it's completely undetectable. But for electrons?
They could prove it.
They did. Davison and Germer showed electrons diffracting off a crystal, just like X-rays, which are waves. It was revolutionary.
And that modern double-slit experiment with single electrons.
Yeah.
That's the really freaky one.
It is perhaps the most mind-bending demonstration. You fire electrons one by one through the slits. There's nothing for them to interfere with.
Right.
But over time, where they land on the detector screen builds up an interference pattern.
As if each electron somehow went through both slits at once, like a wave, and interfered with itself.
That's what it looks like. It completely breaks our classical intuition about single objects having a single path.
Okay, so if electrons and stuff are acting like waves,
Yeah.
how do we describe them? Is there like an equation for these matter waves?
There is. That was Erwin Schrödinger's great contribution in 1926. He developed the Schrödinger equation.
Famous one.
The famous one. It describes the evolution of something called the wave function, usually written as psi.
And what is the wave function? Does it tell you where the particle is?
Not directly, no. That was the puzzle. It was Max Born who figured out the interpretation. The wave function itself isn't the physical wave. But if you square its amplitude, you get the probability density, the likelihood of finding the particle at any given point in space.
Probability. So it's not certainty anymore.
Exactly. That's the huge leap from classical physics. You don't have a definite position and momentum. You have probabilities. The particle is replaced by this cloud of probability.
So an atomic orbital. That's not a path. It's just where the electron is likely to be.
Precisely. It's a map of probability derived from the wave function, showing the region where the electron has a high chance of being found.
Okay, probability clouds. That's already pretty out there. But you mentioned something even deeper, where the idea of a particle kind of vanishes altogether.
Right. That's where quantum field theory, or QFT, comes in. It's our most fundamental description of reality right now.
And what does QFT say?
QFT says that the truly fundamental things aren't particles at all. They're fields. Continuous, space-filling fields.
An electron field,
Yeah.
a photon field, everywhere.
Exactly, permeating all of space-time. And what we perceive as a particle, like an electron, is actually a localized excitation, a vibration, a ripple in that underlying electron field.
Whoa. Okay, unpack that. Like a pond.
That's a great analogy. Think of the field as the calm surface of a pond. That's the vacuum state, the ground state.
Right.
Now, drop a pebble in. It creates a ripple, a localized disturbance that travels across the pond. That ripple is like the particle. It's a quantized packet of energy propagating through the field.
So the wave-particle duality thing, QFT, explains it.
It resolves it beautifully. The field is the underlying wave-like entity spread out in space. The particle is the quantized, discrete excitation of that field that we detect locally. The duality arises because our classical concepts of wave and particle are just inadequate descriptions of this deeper reality.
So reality isn't particles moving in empty space.
No, the fields are the space, in a sense. They're the substance of reality. Matter, forces. That's just how these different fields vibrate and interact with each other. Even the vacuum isn't empty. It's the seething sea of potential, these latent fields ready to be excited.
Okay, fields vibrating. Probability clouds. How does this connect back to the sphere? If everything's so fuzzy and probabilistic, how do we get solid-ish spherical shapes emerging?
That is the critical link. Let's go back to the atom. The old picture, electron orbiting like a tiny planet, totally wrong. Doesn't work.
Right, it would radiate energy and spiral in.
Exactly. Quantum mechanics solves this. The electron in an atom exists as a three-dimensional standing wave.
Like on a guitar string.
Perfect analogy. A guitar string clamped at both ends can only vibrate in specific patterns, right? Specific harmonics, stable standing waves.
Yeah, fundamental tone, overtone.
Right. An electron clamped by the electric field of the nucleus is similar. It can only exist in specific, stable 3D standing wave patterns, and each pattern corresponds to a specific energy level.
And those patterns are the orbitals.
Those are the atomic orbitals. They are literally the mathematical solutions to Schrödinger's equation for an electron trapped in the atom's potential. They're described by quantum numbers principle, angular momentum, magnetic.
Okay, so where's the sphere in these standing wave patterns?
It emerges right at the lowest energy level. The most basic orbital is called the 1s orbital. Its principal quantum number n is 1, and crucially, its angular momentum quantum number L is 0.
L equals 0. Why is that important?
Because when you solve the Schrödinger equation for any state where L equals 0, any's orbital, 1s, 2s, 3s, etc., the resulting wave function, the état, turns out to have a very special property. It's spherically symmetric, meaning its value depends only on the distance from the nucleus, not on the direction. Up, down, left, right, at the same distance, the wave function value is the same.
And the probability cloud.
Since the probability is the square of the wave function, that probability cloud is also perfectly spherical. The chance of finding the 1's electron is identical in every direction at a given distance from the center.
So the most basic ground state electron cloud is a perfect sphere.
Probabilistically speaking, yes. The higher orbitals, like 2s and 3s, are also spherical, just bigger and with nodes like nested shells. But that fundamental orbital shape is the first, most basic manifestation of sphericity in matter itself.
That's incredible. But is it just a coincidence that the math spits out a sphere? Or is there a deeper reason why it has to be that shape?
Now you're hitting on the really deep principle. It's absolutely not a coincidence. It's a direct consequence of symmetry.
Symmetry.
Rotational symmetry. Think about the force holding the electron in the atom, the electric pole from the nucleus. It's a central force.
Meaning it just depends on distance.
Exactly. It doesn't matter how the atom is oriented in space. The force looks the same from all angles. The system is rotationally invariant.
Okay.
And there's a profound connection in physics, formalized by Noether's theorem, between symmetries and conserved quantities.
Right, you mentioned that rotational symmetry links to
Conservation of angular momentum. Now, for a quantum state like the s orbital to have 0 angular momentum, L is 0, it must be completely unchanged by any rotation whatsoever. It has to look absolutely identical from every possible angle.
And the only 3D shape that does that
Is a perfect sphere.
Wow. So the spherical shape of the s orbital isn't just what happens, it's mathematically required by the symmetry of the underlying physical law.
Precisely. It's a physical embodiment of that abstract rotational symmetry. If the electrostatic force wasn't perfectly isotropic, the ground state orbital wouldn't be perfectly spherical.
What about the other orbitals, like P and D? They have those dumbbell and cloverleaf shapes, right? That's spherical.
Individually, no. But here's the kicker. If you consider the entire set of p orbitals, px, py, pz, or d orbitals within a given energy shell, their combined probability distribution, when averaged out, does restore overall spherical symmetry.
Ah, okay, so the symmetry's still there, just distributed differently.
Exactly. And then, if we connect this back to the bigger picture, when you have trillions upon trillions of atoms in a liquid or gas, all oriented randomly,
their individual orbital shapes average out.
They average out, restoring that isotropy on the macroscopic scale. This effectively prepares the ground, creating a situation where those larger-scale central forces, like surface tension or gravity, can then act on this now isotropic medium and impose their preferred minimal energy shape.
The sphere.
The sphere. It creates this beautiful, seamless connection from the quantum rules dictating the shape of the fundamental electron cloud, all the way up to the shape of planets and stars.
That's genuinely profound. The blueprint for a planet is right there in the quantum nature of a single atom. Okay, now let's push even further into the really speculative stuff.
Yeah. The frontiers.
If everything boils down to vibrations, fields, what are the most cutting-edge ideas saying about what a particle really is? And does the sphere show up there too?
Okay, so leaving behind the confirmed standard model, we enter some fascinating theoretical territory. One idea tries to take the wave nature very literally. The wave structure of matter, or WSM, particularly associated with Milo Wolf.
What's the core idea there?
WSM proposes that a particle, like an electron, isn't a point at all. It is a spherical standing wave in the actual fabric of space.
A standing wave.
It's imagined as being formed by two components. Waves converging inward towards a center, in waves, and waves diverging outward from that center, out waves. The particle is the focal point where these waves interfere to create a stable, resonant, standing wave structure.
And it's inherently spherical in this model.
Inherently spherical, yes. It even tries to explain things like quantum spin as related to a kind of spherical rotation of this wave structure. It's quite a holistic view.
Interesting. Very direct. Then there's the big one everyone's heard of, string theory.
Yes, string theory, or M theory. It's modern evolution. This takes a completely different approach.
No spherical waves.
No. Here, the fundamental entities are proposed to be incredibly tiny, one-dimensional vibrating strings, like infinitesimally small rubber bands, either open or closed loops.
One-dimensional. So how do they make particles?
The idea is that the different ways these strings can vibrate their different resonant patterns, like different notes on a violin string, correspond to the different fundamental particles we see.
So an electron is one vibration pattern, a quark is another, a photon another?
Exactly. All arising from the same fundamental string, just vibrating differently. The energy of the vibration determines the particle's mass via EMC.
And its big appeal is unifying everything.
That's the hope. It naturally incorporates gravity via vibration corresponding to the graviton and aims to unify quantum mechanics and general relativity. But it comes with a price.
The extra dimension.
The extra dimensions. To be mathematically consistent, these theories need more spatial dimensions than the 3 we experience, typically 10 in total for superstring theory, or 11 for M theory, which might also involve higher dimensional objects called membranes or branes.
So in string theory, sphericity wouldn't be fundamental to the string itself, but maybe emerge somehow from vibrations in these extra dimensions.
That's the idea. It would be an emergent property, not an intrinsic one like in WSM.
Okay, 2 very different pictures. Is there anything even more out there?
Definitely. There's the bootstrap philosophy, championed by Geoffrey Chew. This is perhaps the most philosophically radical departure.
How so?
It basically throws out the whole idea of fundamental building blocks. No fundamental particles, no fundamental laws or equations in the usual sense.
Wait, what? Then how does anything work?
The idea is that the universe is a completely interconnected, self-consistent web of events and relationships. No part is more fundamental than any other, sometimes called nuclear democracy.
So particles aren't made of anything smaller?
No. Their properties, mass, charge, spin, are seen as emerging purely from the requirement that they must be consistent with all other particles and interactions in the entire universe. The universe essentially pulls itself up by its own bootstraps.
Wow. And sphericity in that view?
It wouldn't be a property of a thing. It would have to emerge somehow as a necessary feature for the overall self-consistency of the entire cosmic network, a consequence of the whole system settling into a stable, coherent state.
So these different theories, they offer totally clashing views on where shape even comes from at the bottom level.
They really do. You have WSM saying the particle is a spherical vibration. You have string theory saying spherical properties emerge from a vibrating line in hidden dimensions. And you have the bootstrap saying forget fundamental geometry, it's all about the consistency of the network.
It really highlights different ways of doing science, doesn't it? Reductionism versus something else.
Absolutely. Bottom-up building blocks versus top-down holistic consistency. And it's fascinating that just asking, why is a planet round, ultimately pushes us right up against these deepest, unresolved questions about the fundamental nature of reality itself. Are there ultimate constituents, or is it all just one inseparable whole?
What a journey. From planets and raindrops down through quantum probabilities and fields to these speculative frontiers. This deep dive has really shown the sphere isn't just common, it's deeply meaningful.
It really ties it all together, doesn't it? You can almost see it as this hierarchy of sphericity.
Lay it out for us.
Okay. At the very bottom, maybe, you have the probabilistic sphere of the quantum's orbital, governed by Schrödinger, rooted in rotational invariance. Probability is equal in all directions.
Right.
Then, maybe, you have speculative ideas like the WSM electron, where sphericity is structural. The particle itself is imagined as a spherical resonance. Moving up, you get the microscopic liquid droplet, governed by electromagnetism, surface tension. Sphericity here is geometric, structural, the lowest energy shape minimizing surface area.
The hamburger bun exception noted.
Ha, yes. And finally, the astronomical scale, planets, stars. Governed by gravity, hydrostatic equilibrium, sphericity is, again, geometric, structural, the lowest energy shape minimizing gravitational potential.
So it echoes up to the scales. But what's the absolute core reason, if you had to boil it down, why the sphere everywhere?
I think it comes down to three intertwined ideas: energy, symmetry, and maybe even information.
Okay. Energy.
Energy. The sphere is almost always the state of minimum potential energy when you have forces acting equally from or towards a center. Gravity, surface tension. Nature is lazy. It seeks the lowest energy state, and that's often the sphere.
Makes sense. Symmetry.
Symmetry. The sphere has the highest possible rotational symmetry in 3D. And as we saw with Noether's theorem, that symmetry is deeply linked to a fundamental conserved quantity angular momentum. The sphere is nature physically manifesting this profound symmetry.
And information. That's an interesting one.
Well, think about how much information you need to describe a shape. For a perfect sphere, all you need is its center and its radius. That's it.
Minimal information.
Minimal information. To describe a lumpy asteroid takes vastly more data. So nature's tendency towards low energy often goes hand in hand with simplicity, symmetry, and maybe even informational efficiency. The sphere embodies all of that.
It really is incredible how just looking at a common shape can lead you down this rabbit hole through basically all of physics.
It truly is. The sphere isn't just some shape nature happens to use a lot. It's a fundamental pattern that reflects the very structure of physical law. The fact that it shows up consistently, from the quantum probability cloud to a giant star, is powerful evidence for these unifying principles of energy minimization and symmetry.
So the shape emerges because of the underlying physics.
It's a profound causation, yes. The quantum waves vibrate according to laws. Those laws possess fundamental symmetries, and those symmetries, particularly rotational symmetry, directly command the emergence of the sphere as the state of equilibrium and minimal energy. It's woven into the fabric of reality.
Wow. Well, what an incredible journey we've taken you on today. From those quantum whispers, the vibrations defining matter itself, all the way up to the giant celestial orbs hanging in the cosmos. And seeing how they're all linked by this simple yet profound principle of the sphere really does make you look at the world a little differently.
Hopefully.
So here's something to ponder as we wrap up. What other seemingly simple observations in our everyday world, things we take for granted, might hold equally deep, unifying secrets? Secrets just waiting for us to trace their origins all the way back, perhaps, to the fundamental symmetries that govern the entire universe.